Hi, this is David Scher. I'm here for the final lecture in Physics 572, Introduction to Health Physics. This is the last week of classes. So we've had a long run, and today we're going to wrap all of it up. I hope it all makes sense when I'm done with this today. So here is our video, our slides for today. And so this is today what we're going to talk about is the different, wrap up the things I have not yet covered. We're going to talk a little bit like of a review of everything, see how everything fits together logically, and then talk about the different areas that health physicists practice in, and how all this information we've learned is useful in different contexts. So here's a little summary of what we talked about. We began with a review of atomic structure and radioactivity and some basic physics. We talked a little bit about the interaction of charged particles with matter, the interaction of photons with matter. So we learned all about the stopping power, the mass stopping power, the various attenuation and energy absorption coefficients, and how radiation or how energy is transferred from radiation to matter. We talked a little bit about biological effects of radiation. We talked a good bit about acute radiation syndrome, something that's pretty severe but not very common. We talked a little bit about stochastic effects like cancer and that sort of thing. Then we moved into areas, we talked about external dosimetry. These were all the calculations we did about fluence and the energy absorption coefficient, mass energy absorption coefficient gives us the dose for photons. The fluence times the stopping power gives us the dose for charged particles. We talked about internal dosimetry, talked about the whole formalism of how the doses are calculated. And we talked a little bit about the tables that we use to get dose coefficients. If we have an intake that we know what it is, we can how much activity is taken in, we can find out what the radiation dose is. Then we moved into the system of radiological protection, learned about justification, optimization, limitation, what the dose limits are in various scenarios. Then we talked a little bit about regulations and radiation detection and measurement. Now, in the curriculum that you're going to be part of, the first portion, atomic structure, radioactivity, we're going to go into more detail on that in Physics 571. I think many of you have taken that, but some of you have not. Same for charged particles and photons. We have a whole course on biological effects of radiation at a more fundamental level, the biophysical level. We have a course in dosimetry in our program that covers both external and internal dosimetry. We have a class on standards, regulations, standard statutes and regulations that covers the system radiological protection, the government regulations that are developed on the basis of that. We have a course in the summer for radiation detection and measurement. We talked a little bit about it, but you'll come to, if you're continuing the program, you'll come to the campus in Chicago and play with a lot of radiation instruments and learn how to measure radiation. Then so as a result of all of that, we recently started going into the applied science of radiation safety, how this stuff gets applied in practice. I just mentioned that I put a video in Panopto earlier this week that has a number of examples of calculation of external exposure. So for external exposure, we have 3 ways to limit exposure: time, distance, and shielding. If we limit our time, we limit our exposure. The farther away, the lower the dose rate is, and more shielding, the lower the dose is. Then, as I said, I have apparently an hour-long video on shielding designs with several examples. specifications, so how we choose what our design goal will be, and then calculations to determine the amount of shielding material necessary to achieve that. In some cases, it can be pretty complex, as you will see it on the video. Then the other area where we can apply all the science we learned is for internal exposures. So we have two worlds. We have external exposure and internal exposure. And I'm going to briefly cover this in a few slides. The first method that we choose for managing internal exposure is by engineering design. We design ventilation systems to limit exposure. That's preferred over procedural or practice limitations and over use of PPE. PPE, personal protective equipment, which is our next item, should only be used for the residual hazards that can't practically be eliminated by engineering controls. Engineering controls are more reliable and work without, it's more difficult to circumvent or to forget. The ventilation system operates or should operate effectively without you having to remember to do anything for it. That's the goal, at least. Personal protective equipment is used for residual hazards, as I just said. And PPE includes things like clothing and gloves to prevent skin contamination or transfer of skin contamination to for ingestion, and also respirators. And so in the area of airborne contamination, this is what we're going to talk about for a few slides. Okay, so respirators there are a few types of respirators. There are air purifying respirators that filter the air that's in the environment. And so air purifying respirators are like what are popular known as gas masks, typically. They are most useful for particulates. There are filters that of very fine size that can remove most particulates. They're not as good for removing gases because gases can pass through the respirator just like the gases in the air do. There are cartridge respirators that can be used for some vapors. For example, there are cartridges for aromatic hydrocarbons that can be used, but they're only good for the chemicals that they're designed to filter. In addition to purifying respirators, the other class is supplied air respirators. They basically, supplied air respirators are just what they say. They supply air to you from some other source, not in the immediate vicinity. And they can be, they do protect against particulates because the air is coming from somewhere where the particles aren't in the air, but they also protect against vapors and gases because you're not breathing the air in the hazardous environment that's arising from the hazardous environment. Now, respirators can be either negative pressure or positive pressure. So a negative pressure respirator, filtered air purifying respirators are typically negative pressure, or many of them are. So you breathe through a filter and it's negative pressure because you're sucking in the air. And so the pressure inside the mask is negative relative to the pressure in the environment around it. There can be either continuous, for supplied air, there can be either continuous or demand. So either the air is supplied all the time, continuous air supply respirator, or only on demand, only when you inhale, then air is provided. The masks associated with the respirators can either be full face, covering the entire facial area, or just half face, just the breathing zone, and they have different effects. Okay, so that's respiratory protection. Now, for each kind of respirator, there's an assigned protective factor. This is effectively how much of the material is removed, what ratio of the material is outside the respirator compared to what's inside the respirator. The respirators are approved by NIOSH. It's a government agency. The procedures for approving them are this is the regulation that specifies that. Let's see. NIOSH provides this information to other government agencies, and OSHA publishes a pamphlet with the assigned protective factors for respiratory protection. So you can get all the information about this. Is a half-faced demand respirator. It looks like it has cartridges for some particular vapor. This is a full-faced respirator. This is a powered air purifying respirator. So it's taking in air from the environment and purifying it, but it's powered and blows through the respirator. Instead of being negative pressure, it's a positive pressure system. These are different kinds of respirators. So we use these in radiation safety, just like industrial hygienists use it for chemical hazards. Let's see. They're published by OSHA, and the regulations for radiation control, either for the NRC or for the Department of Energy, also reiterate what these approved protective factors are, so you don't have to go look elsewhere for them. Let me see if I can find, no, where did I put those? Maybe it's this one. Yeah, so here in 10 CFR, Part 20, Appendix A, we can find the assigned protective factors for respirators. It's basically reiterating information on what NIOSH has found. They're broken down into air purifying respirators, atmosphere supplying respirators, and they also come in operations. So air supplying, there's airline respirators, which are the same kind of mask that is used otherwise, or there are self-contained breathing apparatuses, which are just what they say, they're self-contained. So they're tanks of air that are provided in provide the worker in the hazardous environment with air that's not coming from the environment. So that's where you find the APFs. I'm going to use an example. Recently, in recent years, we've heard a lot about N95 respirators. They're used in the healthcare industry. So I'm going to try to explain how this rating system works with the example of the N95 respirator. In this case, the N means not recommended for oil environments. It will break down or become less effective if it's used in an environment where hydrocarbons are in the atmosphere. The 95 means it has a 95% reduction in particulates, and 0.3 microns is the diameter that they use for reference. So if 95% reduction, that means that the amount that is transmitted is 5%. That's the 0.05. If we look at the reciprocal of 0.05, that's 20. So the APF for an N95 respirator would be 20. Clear enough? Okay. Hearing no questions, I'm going to move on. The respiratory protection program involves things other than simply identifying the respirator and knowing the assigned protective factor. If you're going to have a respiratory protection program, you're required to have medical evaluation for everybody that's going to be included. Respirators place a demand on people's breathing, and it can be hazardous to people who aren't medically capable of using them. So there needs to be some medical evaluation to make sure that people are not going to be injured by using respirators. Program requires training. People need to know how to use these things properly, how to don them and doff them safely. There has to be fit testing. So the respirators, particularly negative pressure respirators, have to have a tight seal to the face, around your face. You can't have beards like me. So I'm not, with this grooming, I'm not able to wear a negative pressure respirator with that would be appropriately fit tested. Every
So
day.
we'll, in an emergency, we'll hand you a razor and shaving cream and it won't be high quality.
Yeah, and I'll be breathing in all that stuff while I'm shaving. So, okay, I could just use a PAPR. So a positive pressure respirator would work. Although they're kind of expensive. So every time you put on a respirator, you need to do a seal check to make sure that it is actually filtering all the air, none of it's leaking in through the side. It's important. There need to be procedures for cleaning respirators. You're using them in a contaminated environment. That's the whole idea. So contamination can be present on the outside. There are so people need to be trained on how to clean them properly, and then maintenance of the respirator. In addition to cleaning, there's an ongoing checks and maintenance whenever there's is necessary. Now, I want to mention that we've talked about external radiation. We talked about internal radiation exposure. And so in an overall safety program, when we're trying to keep exposures as low as reasonably achievable, so we're optimizing exposures, there are times when these two hazards compete against each other with regard to safety. So sometimes a job requires more time, a particular task requires more time to perform when wearing a respirator compared to doing it without a respirator. And so if we reduce the internal exposure, we may increase external exposure because we have more time in that workplace. So we have to have a way of competing balance all the competing demands. And I'm going to work out an example of a situation where a worker needs to be in an environment to do a task for that's 20 millisieverts per hour. So for those of us who've been around a while, that's 2 rems per hour. It's a relatively high exposure rate. It can't be reduced for whatever reason. And this is not a long task. You'll see. In this environment, however, there is airborne strontium-90. I picked that because I think we've used that DAC before. And the concentration measured in the area is given right here. Okay, so I'm going to switch to my latest toy I've come up with. And when you see my videos of the examples I worked, you will see this. I have, can you see it or no? Do you see a writing tablet? And okay, so I'm going to work out the example. Here's a problem. We have a problem with external exposure, 20 millisieverts per hour, 2 rads an hour, and airborne activity. I'm going to use, say that this is Y class, strontium-90. And so let's see if I can find it here. We just had I think it's here. It's not there. It's here. There we go. So on this page, I have this. I happen to, I've already looked at this. So I went to 10 CFR 20. This is in 10 CFR 20, Appendix B. That's where all the alleys are. I went to the isotope. So this is 10 CFR. I went to the isotope for strontium-90. And I found out what the DAC is. When we're doing air monitoring or air exposure, the most straightforward way to do the problem is using DACs. That's the essentially the standard. There is a way to convert DACs to alleys based on breathing rate, but we're going to work with the DACs today. And this is Y class. So this doesn't have a tissue indicated. So this is for the effective dose equivalent, committed effective dose equivalent, whole body dose, and it's 2 times 10 to the minus 9. Okay, so on my pad I have a DAC I have not indicated it here. So the DAC is 2 times 10 to the minus 9 microcuries per milliliter. Let's make sure that we've got that right. Two times 10 to the minus 9 microcuries per milliliter. There we go. Okay, so how do we go about solving this problem? We're going to have two kinds of exposures. Okay, let's first look at what our concentration is compared to the DAC. Okay, so our concentration is 4.3 times 10 to the minus 6 microcuries per milliliter, and the DAC is 2 times 10 to the minus 9. They're the same units. Good, that checks out. So let's divide these out. 4.3 times 10 to the minus 6 divided by 2 times 10 to the minus 9. 2150. That's what it is. Our concentration is 2,000 times as high as the DAC. But it's only for a short period. For the task they need, if they wear no respirator at all, the task could be completed in 30 minutes, half an hour. If they wear a full face negative pressure respirator, the task is 45 minutes. And if they wear SCBA, so that's supplied air, it's a pressure demand respirator, the task takes 60 minutes. It's just more difficult to achieve. So going back to my APFs, wrong one again. Here we go. So we had a full face NPR, full face negative pressure respirator. The APF is 100. So with no respirator, there's no APF. With a full face negative pressure respirator, it's 100. And with SCBA, we've got pressure demand. So it's 10,000. Okay. So we've got our APFs here. So we've got three problems. We've three situations. One is we have no respirator. One is if we use an APR. And one is if we use an SCBA. So what are the components? One is go ahead.
Can you minimize the Appendix A so we can see the page you're reading?
Oh, yeah, thank you. I have a tendency to not look at the screen. So here are my APFs. That's just what I copied. So three scenarios: no respirator, wearing an APF, wearing a SCBA. So the first component is external. And so for no respirator, it's 2 rads times 30 minutes, or 20 millisieverts. I'm going to do this in millisieverts per hour, or millisieverts. 20 millisieverts for half an hour, that's 10 millisieverts. Okay, with a negative pressure respirator. With a negative respirator, it's 45 minutes. So it's 0.75 times 2. So 0.75 hours times 20 millisieverts per hour is 15 millisieverts. And with an SCBA, it takes an hour. So it's 20 millisieverts per hour times 1 hour is 20 millisieverts. Okay. Now, to do the DAC calculations a little more complicated, we have to first look. We've got the fraction of a DAC, and now we have to calculate the DAC hours. So we have 2150 DACs times a half an hour. So 2150 divided by 2 is 1075 DAC hours. Okay, with the negative respirator, air purifying respirator, negative pressure respirator, it is 2150 times, it's 3/4 of an hour, 0.75 DAC hours. So 1612, 1613 DAC hours. And for SCBA, it is a full hour So it is 2150 DAC hours. So it's 2150 is the concentration times the time is the DAC hours. That's 1 hour. Okay, now let's figure. So we have our APF that we're going to need. That's 1. APF is going to be 100, and it's 10 to the 4. So now we're going to get the committed dose equivalent, or it's actually committed effective dose because this is whole body exposure. So I take my DAC hours to get that, to get the CEDE. It's DAC hours times, okay, so it is, this is whole body effective dose equivalent. So that is 50 millisieverts is the standard for 2000 DAC hours. That's what, so 2000 DAC hours will produce 50 millisieverts. So we scale our DAC hours by 2000 and multiply by 50 millisieverts. So I've got 1075 DAC hours times, well, I'm just going to do the 50 over 2000 once. And that is 0.025. So that's how our conversion factor from DAC hours to sieverts. We still have to remember the APF. So 1075 times 0.025, which is gives us the sieverts, it's 27 millisieverts. Okay, now we have 100 DAC hours, 1613. In this case, the case of the negative pressure respirator, times 0.025. Then I divide it by 100 because that's the protective factor, the sign protective factor for the radiator, and I get 0.4 millisieverts. And the SCBA is 2150 times 0.025 times divided by 1 times 10 to the minus 4. It gives me not minus 4. I'm do it all over again. 2150 times 0.025, that's our conversion, divided by 1 to 10 to the 4th. It gives me 5 times 10 to the minus 3 millisieverts. So what's our total? In this case, it's 37. It's 10 from external plus 27 from internal exposure, 37 millisieverts. In this case, 15 plus 0.4. So we'll call it 16 millisieverts. And this is 20 plus 0.005. We'll call it 20 millisieverts. So even though we have a very high concentration, it's 2000 times the DAC. Going to the highest respiratory protection gives us more dose than if we go to a moderate level of respiratory protection. So if we were overly concerned about internal exposures and we put the person in the SCBA, they'd end up with a higher dose than if we just had them wear a negative pressure respirator. And the highest dose of all comes from just wearing nothing, just going in and doing the job as quickly as possible. Okay? So this is how we go about doing a job hazard analysis and deciding what kind of protection is necessary. Any questions on this example? I hope that the people watching by video don't have any questions either. You may see this again in the coming days, this kind of calculation. You may also see a shielding kind of calculation that I did on the other videos coming in coming days. So that's where we are with that. So this is the kind of calculation that HPs do. I wouldn't say routinely, but it is the center of the kind of work we do. Okay, now I want to talk about areas where HPs practice. And some of you may practice in these environments, and I'd like to hear your feedback about this. one area where health physicists practice is in the fuel cycle, facilities that are part of the fuel cycle. I'm going to briefly describe this and the kind of work they may do. So what HPs do, they use the same science in different industries. And so to be an effective member of any employment situation, you need to have an appreciation of the overall job that's being done and your place in it. And so we're going to try to describe the overall work that's done by different facilities in the fuel cycle and what health physicists do there. So the first is uranium recovery. This is mining or in situ leaching of uranium from the soil. Health physicists are involved because this kind of work can produce a lot of contamination after as materials are being removed from the soil, because wherever uranium is, the daughter products of the uranium chain are there as well. So as materials are removed from the soil, along with it comes a lot of other radioactive contaminants that can cause problems. The largest concerns here are not necessarily the external exposures, it's more contamination control for the uranium recovery process. Milling is where the mined material is the rocks, the ores that are mined out are milled into fine smaller sized particles, and the material is removed, the uranium is removed through chemical processes from this. This leaves behind tailings, the leftovers, the waste, the byproduct material of this process. And that's an environmental hazard because it can leach into the soil and affect people in that site for years to come. So uranium conversion is then taking the material, the uranium oxide that's gotten from the ores, and convert it into yellow cake, which is an oxide. So from UO2 I think it's to UO8, and then U2O8, something like that. And the the uranium is then sent off to plants where it's converted to uranium hexafluoride, UF6. This is a gas. The uranium gas is then used to separate out the different isotopes to enrich uranium-235 and leave behind U-238. The hazards in this work environment are largely respiratory. Uranium doesn't have a large gamma ray dose. It has some beta ray dose, but largely the hazards associated with uranium are and uranium conversion facilities or enrichment facilities are from gas that might be leaked. The enrichment facilities, conversion and enrichment. The enrichment facilities try to collect the enriched uranium with different degrees of enrichment. Different levels of enrichment are used for different purposes, and then separate out, also collect the depleted uranium, the uranium that's enriched in U-238, depleted in uranium-235. That's a waste material. As far as the fuel cycle is concerned, depleted uranium can be used for other purposes, like conventional weapons by the military. It's used for penetrators, it's used for shielding, it's used for ballast. It's very dense. The small sizes can add a lot of weight to balance out aircraft and other things. But that's uranium enrichment. The enriched uranium is then sent to a facility for fabrication into fuel. So again, the new uranium fuel is not very radioactive, or doesn't have a high exposure rate at the surface. But the concerns here are the fabrication process involves a lot of potential contamination, and so those facilities, health physicists at those facilities, work with largely contamination control, respiratory protection, and that sort of thing. So the fuel is fabricated into fuel rods. Those rods are sent to reactors. The reactors are part of the process. That's the utilization portion of the fuel cycle. I'm going to describe how reactors work in a moment, but health physics working in reactors, there are a large number of them that do many, many tasks. Part of it is health physics for the technical staff who work there. Part of it is concerned about effluent monitoring so that the people who live around the power plant are safe. There are health physicists who work in monitoring the chemistry, et cetera. There are a lot of tasks that are associated with this. The fuel, as it becomes, is used more to undergoes more of a nuclear reaction, more and more fission products. That's described in the next slide, but it gets more and more radioactive material of a different kind as a result of the process. These byproduct materials, these fission products, poison the nuclear reaction, so it can't be used for fuel anymore. It still has most of the uranium left in it, along with a lot of other isotopes that give off a lot of radiation. Those fuel rods, when they're no longer useful, had to be put into storage. First in pools until they decay, and then into dry cask storage. They have to be stored in dry casks because in the United States we have no central repository for these. So all of the fuel that's ever been produced is either on the power plant site or on a commercial fuel storage location. We do not reprocess fuel in the United States. That may happen for military applications where the uranium, as I said, the fuel has most of the uranium that it started off with still in it. It also has produced plutonium in the process of being the fission process, so that uranium can be removed. The uranium could then be returned to the feedstock and be used again to produce more fuel. The plutonium can also be used to produce fuel. This MOX fuel that's mentioned here is mixed oxide fuel. It contains both uranium and plutonium. Waste material that the byproduct materials that was produced originally has to be, and any contamination that results in the plant. There's lots of contamination that occurs in nuclear plants. That material is sent for disposal, and so that's another part of the fuel cycle. Okay, so lots of different kinds of work environments where we use our skills at assessing radiation hazards and controlling them. Do any of you work in a fuel cycle facility? Just raise your hand on there if you like. Nobody who happens to be here today, apparently. Okay, but there are a good number of people who work in this area. Now, basically, the way nuclear reactors work, the fuel rods are placed in water, ordinary water. There are two designs. One, this is a boiling water reactor. So the fuel rods are placed in water. Water serves as a moderator to slow down, to absorb energy from neutrons. Uranium gives off neutrons. They're slowed down and they're absorbed by other uranium atoms. And when they do, the uranium nucleus splits into two new products. It produces two different elements and also releases neutrons. And so that the radioactive material, the fission products build up in the fuel. They have to be cooled by the moderator also serves as the coolant. So the water that's heated up becomes steam. The steam is carried off. It turns a turbine and generates electricity. Once it's turned its turbine, it's used up some of its energy for the turbine. It's then cooled by an outside source, usually a lake or a river or an ocean in some cases, to get rid of the residual heat. It turns back from steam into water, and it's returned back to the reactor, and the cycle continues. That's a boiling water reactor. Pressurized water reactors are very similar. In some aspects, the nuclear fuel undergoes this chemical decay, chemical reaction that gives off energy and produces radioactive material. This produces very hot steam, but it's held under pressure, so the steam is kept as water. That water is then passed through a heat exchanger. So the very hot water runs through small tubes. Another loop of water, a separate loop of water, comes in. It's heated by the tubes in the heat exchanger, produces steam, and this loop runs off and goes through a turbine to generate electricity. It's also excess energy. The heat is removed again from a cooling tower or a lake or a river or some heat sink. The very hot water that went through the steam generator is then returned through the reactor again. It has lost some of its heat and is heated up again because of the nuclear reaction. So a nuclear power plant is basically a steam factory. We use nuclear reactions to produce steam. That steam is then sent off to produce electricity. Now, the two-loop design of the pressurized water reactor was thought that it would result in less contamination outside of the reactor itself, because ostensibly we have a dirty loop and then we have a clean loop that goes off to the generator, whereas in a boiling water reactor, radioactive water goes off to the generator and other parts of the plant. That was the principle. The problem with that is that steam generators have very small tubes and they often develop leaks. They're operating at high pressure, and so the water that's on the secondary loop that goes to the turbine often becomes contaminated anyway. And so health physicists have to be involved in assessing hazards associated with the reactor itself, with the cooling water, with the other parts of the plant where people have to do jobs. Do I have any questions about reactor operations? Any critique from the nuclear engineers in the audience? Okay. So the reaction that takes place that produces all this energy is a fission reaction. Uranium-235 absorbs a neutron. It becomes very unstable nucleus, U-236. This splits into two smaller parts, and these smaller nuclei that are produced are and can include very many radioactive isotopes. In addition, there are on average 3 excess neutrons that go off to create new reactions in the with other uranium nuclei in the fuel. Another source of radioactive material in power plants is activation products. So cobalt-59 is normal stable cobalt. It's used in a lot of places in the power plant because it's a component in some forms of steel. And so work that may be done, maybe grinding a valve or so it seats properly, may produce very small fragments of cobalt-59, dust that may circulate through the reactor. If cobalt-59 absorbs one of these neutrons, it becomes cobalt-60. We've talked about cobalt-60 before. It has a very high energy gamma, 2 gamma rays per decay, about 1.25 MeV between them. And so it's a major contributor to dose in power plants. Both of these, fission products and activation products, are part of a class called byproduct material, and that's because they're byproducts of reactor operation. I mentioned that there was, in the fuel cycle, there was byproduct material as a result of the mining and milling operations. That's a different kind of byproduct material. Okay, so where else do we health physicists work? Another group of couple of different sites where health physicists work are in research institutions and in industry. In research is often done under what's called a broad scope license. So when someone gets a radioactive material license, they have to they are limited to the operations that are spelled out in the license. But when you're doing research, you're developing new knowledge all the time, and as a consequence, new procedures and new processes are required all the time. So in a broad scope license, the institution can make those decisions instead of the regulator making those decisions. And so health physicists who work in broad scope environments have to, particularly in research environments, have to be very flexible and able to use their basic science knowledge to deal with situations that have never been encountered before. It's not like other kinds of operations, other kinds of activities. The work in power plants has been done for many, many years. The NRC has a lot of guidance documents that tells you exactly what to do. It's complicated to apply, but it's not new, it's not novel. You're doing things that have been done before. The same is true in medical applications. There are numerous guidance documents from the NRC on how to handle the issues that come up in medical applications, because there are a lot of people doing it, and it's the same problems everywhere. The thing about research is that the new problems that occur only at one place. One professor is doing this kind of work. It doesn't become something that affects a whole industry. And so you have to, a broad scope license, you have to be able to manage these things. You have to have processes in place to make these decisions. As far as industry goes, there are some examples. Industrial radiography is an example of an industry that uses high radiation sources. These are using sealed radioactive sources to take x-rays of construction operations, either welds, for example, in structural steel or in pipes, to make sure that they're going to be effective. This poses a risk to the workers who are doing this, and potentially to other people who might be in the area. So health physicists are involved, and radiographers themselves have very strict procedures that need to be followed to do this work. Radioactive materials are used in process and thickness gauges. So radioactive materials, radiation is, gamma rays are penetrating, and the amount of absorption that takes place is dependent on how much material they pass through. So radioactive material, radiation sources are very effective for measuring the thickness of some material that's being produced, for example. And so they're used for that purposes. Another place in kind of industry where radioactive materials are used are sterilizers, either using high energy gamma sources. One of the examples I did of the exposure problems and the shielding problems was a gamma irradiator. In addition, there are electron beams that are used for sterilizing, so it's a different kind of dosimetry. They're used for sterilizers in a number of settings. There are people who produce radiation sources, either these sealed sources that are used for gauge thicknesses, the sources that are used for industrial radiography, or all kinds of other sources, standards that are used for measurement, pharmaceuticals that we're going to talk about nuclear medicine in a little bit. So there are industrial facilities that produce all the radioactive material that's used in nuclear medicine, for example. So there are lots of different environments. It's important to understand the business that's done and how the radioactive material is produced or used, so that you can be effective at advising workers on how to keep themselves safe. I mentioned medical health physics. In the hospital, there are a number of different kinds of radioactive radiation sources. One are X-ray sources that are used for taking X-ray images, either static phototype images called radiography, or dynamic images like a movie called fluoroscopy. They pose different risks both to the workers and to the patients. Mammography is of concern because exposures are to radiosensitive tissue, and very demanding imaging techniques. It's very difficult. We're looking at differences in density of very small differences in density that have to be observed. Computed tomography is another type of X-ray source used in hospitals. This is basically an X-ray source that's used to get a 3D image, but it ends up requiring much more radiation than a plain film photograph type imaging does. So those health physicists need to be involved in working with the staff who works on all these radiation sources in diagnostic imaging. In addition, I mentioned nuclear medicine. Nuclear medicine is where we use radioactive materials to inject into a person, or they may ingest it, this material, both for forming images. So we may inject a drug that goes to the bones that is labeled with some radioactive material. The drug carries radioactive material to the bone, and then we can make an image of the bones. We can have a drug that goes to the liver. We label it with radioactive material. The drug goes to the liver, brings radioactive material with it. We can image the liver, the functioning of the liver, how much of the liver actually absorb this chemical. In addition, in nuclear medicine, there is work that's done with radiation therapy. Sometimes we can treat disease by delivering a large radiation dose. For some cases, that may be about ingesting or injecting radioactive material into the patient. And the material will, again, just like in imaging, it may accumulate in a particular organ or for a particular cancer. And we can attack that tissue with the radioactive material. And so there are lots of contamination issues and external exposure issues for the hospital staff and for the people when the patient goes home. A third class in medical health physics of radiation sources we have to manage are in radiation oncology. This is the use of radiation to treat cancer largely. There are two types of radiation oncology that's done. One is external beam, where a linear accelerator or a high energy X-ray machine will produce X-rays that we use to target to a particular volume where the tumor would be, and we can, by using multiple angles where the beam goes through different, it's spread out with lesser amounts in the healthy tissue, but all those beams cross at the target volume. We can deliver a high dose to the target volume and less to the surrounding tissue. Brachytherapy is the use of sealed sources for radiation therapy. And so small sealed sources can be placed very close to the tumor or embedded in the tumor and deliver high doses. These sources can be either temporary or permanent. They can be placed in the patient for the rest of the patient's life, essentially. So health physicists work in this environment to support all these operations and keep staff and members of the public safe, and have some operations that work with patients as well. Largely work with patients is left to the physicians, and a discipline that's related to ours called medical physics. It's similar to health physics, but it's a little bit different. Anybody have any work in medical health physics environment?
Yeah, I'm in medical health physics.
Right. So you have anything to add to what I've said?
Not really. Just, I mean, there's kind of a lot of overlap between,
Right.
All these nuclear medicine and oncology and radiology all kind of overlap in a lot of places.
And I didn't even mention cardiology, did I? So some of the highest doses in the hospital are for people who aren't radiologists, people who are cardiologists who you've heard of cardiac catheterizations. They're images, fluoroscopic, so dynamic images taken of the heart. They place a catheter in a vein, snake it through the body to the heart, and inject iodine, a material that absorbs the X-ray so they can see the blood vessels around the heart. These procedures involve relatively high quantities of radioactive or amounts of radioactive material, and involve relatively long exposures, and so they can be hazardous for the patient and for the physician, because the physician is doing one after the other after the next, and the staff that works with the physician, the technologists and nurses. So that's a big concern for medical health physics as well. There's a related area called interventional radiology where they do the same kind of operation, just in other parts of the body than the heart. So they might be used for brain aneurysms, or it might be used to drain an abscess or something, where all that work is done under fluoroscopic guidance or with CT scan, while CT scans are done to make sure they've treated the correct place. And they involve large exposures as well. Is that right, John?
Yeah, that's definitely right. All of our highest doses, when you look at dosimetry, they're all cardiologists.
Yep. It's their bread and butter. There are some cardiologists who do nothing but interventional cardiology. They do nothing but catheterizations over and over and over again. So they're going to end up with large doses. There are other cardiologists who just do medicine, just see the patient in the clinic and don't do the cath work. So that leads to a concentration of exposures in a small number of people. Another area of practice is environmental health physics. This is, my first line may seem a little bit obvious, but this is all about radioactivity in the environment. Why it's environmental health physics. So from these various sources that we've worked with, whether it's nuclear power plants, whether it's waste disposal facilities, whether it's DOE facilities. So when in the past, when weapons were being produced at a high rate, there wasn't as much attention paid to the long-term negative effects of storing material. And so there's large projects that are underway to remediate those facilities. So environmental health physics have a more in-depth operation of air, water, and land deposition, how the radioactive material will move through the air, how it will move through the groundwater or the surface water, and how from either of these mediums, how it's deposited into land. And from there, it could be transferred to crops that we may eat. It could be transferred to plants that animals eat, that we then eat, etc. And so it's about assessing the dosimetry of all of these different environments. Another area of interest in environmental health physics is dealing with future contamination. So when a facility has worked with radioactive material is going to be closed, then that facility needs to be decommissioned effectively so as to protect future generations. And so those decommissioning and decontamination decommissioning procedures or operations are part of the whole area of operational of environmental health physics. They're also the safety for the workers doing the decommissioning work is operational physics, but the guidance for when is a facility clean enough, there's a manual called the Marson manual that talks about how we do this work or provides guidance on how we do this work. That's all I think under the rubric of environmental health physics. Anybody here work in environmental or D&D work? Great. Okay, now I want to mention that we have a class. So this material that I've just briefly talked about is dealt with in more depth in other classes in our program. We have a class in operational health physics to talk about all of the processes for building an operational program, which would apply across the board. It would apply in fuel cycle facilities. It would apply in power plants. It would apply in industry. It would apply under broad scope licenses. All the considerations that go into an operational radiation safety program, from training to monitoring to contamination surveys to a wide variety, what to do with accelerators, all these things go into operational health physics. We have a class in medical health physics that talks about all these things that I just mentioned very briefly in much more depth. We have a class in environmental health physics that talks about the transport models that we've been talking about. We also have a specialization in our program, a group of classes that are dedicated to radiochemistry. So radiochemistry is the use of chemical techniques with radioactive materials. It can be radiochemistry can include sample preparation or purification of materials, an analysis of samples. Radiochemists have to have in-depth understanding of radiation detection and measurement systems. We talked briefly about gas-filled detectors. Radiochemists use other detection systems that are very sensitive and very they have a great deal of specificity, so they can identify particular nuclides with great accuracy. Radiochemists work in fuel design, in fuel reprocessing, and waste management, all the things we talked about related to the fuel cycle. And as I said, there's a specialization in our program for people who want to work in that area. Emergency response and security is another area where health physicists work. A number of government employees are prepared to respond in the case of an emergency, to provide protection for the public, to monitor dangerous situations or off normal situations, and advise the public what they should do to protect themselves. These are from nuclear facility accidents and also from nefarious actors. Radioactive dispersal device is RDD. It's called a dirty bomb. So it's possible that a terrorist or some nefarious actor could get a hold of radioactive material and explode it with a conventional explosion so that it disperses radioactive material along in some important location that would create havoc and panic in the public. Another place where where health physicists work in emergency response is providing advice during an emergency for the protection of first responders. So there are people who have prepared for that. There's a program, let's see if I've got the slide for it, that the Department of Homeland Security is ramping up, called the ROST program. I think I have one. Maybe it's in here. I had a slide for this, maybe. Let me see if I can find it. Not there. I don't have it. So the ROST program is sponsored by the Department of Homeland Security. What I can do. I can get it again this way. Radiological Operations Support Specialist. So this training is offered at some HPS sites and some other meetings. It's training on how health physicists can integrate with the emergency response incident command structure and provide guidance for the workers, the firefighters, the policemen who are responding to emergencies to help keep those people safe. We have a program that's intended to train people for emergency response. In addition, this program works with in terms of security planning, of preparing, understanding methods to prevent people from gaining access to radioactive materials, people who should not have such access. And so there will eventually be courses in both emergency response and in security for this specialization. Okay, now as working health physicists, we so the way how do we build our career? Well, first we gain technical competence, and many of you are already working in health physics, and I assume that enrolling in this program at Illinois Tech is a way to increase your expertise, your knowledge of radiation safety, to prepare you for more responsible positions. In addition, experience is invaluable. In addition, no matter how much you learn at an environment like Illinois Tech, you're going to learn more and gain more judgment and more appreciation for how to keep people safe from actually working in the field and working in different positions with different levels of responsibility. Another thing that's important for professional development is networking. That's a buzzword these days, but get to know other health physicists. They can help you with problems. You can help them with problems when questions arise. In addition, this is a way. One form of networking is maybe going to annual meetings or professional meetings. You're going to learn new things that have been discovered, new standards that have been developed, new techniques. So that's going to be important for professional development, is becoming a lifelong learner. And then one way to demonstrate your competence and all the experience you gain is through certification. Certification is based on a combination of educational background and experience. Almost all certification programs require both. The one that's probably most important in our area is the American Board of Health Physics. And so you should look into that. There's another certification in our field called the Registry of Radiation Protection Technologists that register radiation safety people at the technician level, more of an operational level, not as much theory as the ABHP operates at. There are certifications in fields that are adjacent to health physics that are work in the same area. I've seen a number of health physicists certified in safety. So a board of so they become, well, industrial hygienist is one way, and the other is safety professionals. So certified safety CSP is another direction people go. There are certifications in hazardous materials that deals more with chemical hazards and radiation. Anyway, gaining certification is a way to demonstrate your competence. Doesn't mean the people who are certified are the world's experts. They just demonstrated that they have a level of competence to be able to operate independently. And that is what I have for you on slides. Do I have any questions at this point? Okay, so the exam coming up. Let me advise you that you should look at the example I worked today. You should look at the video that I prepared earlier this week that is about calculating shielding, how to calculate the shielding required, or the shielding that, how much shielding material provides, including the use of buildup factors. That's somewhat complicated. I will probably not ask you to figure out how much thickness is required, including buildup factors, because it's an iterative process and can take quite a long time. So I would focus on those. That's going to be the bulk of the test. I may ask a few questions. Well, I don't really want to make this a comprehensive exam, so I'm not going to ask for the whole semester, but I may ask some key questions that I went over in this review that are central to health physics. I'm not going to ask you specific questions about arcane details about atomic structure or something like that, but something about how health physics is practiced and some scientific material that's pretty fundamental to health physics. Are there any questions I can answer for you?
So the main things for this test are the shielding and then what we went over today with like a aspects of health physics as a field.
The shielding, the one I did on respiratory protection, weighing off shielding versus contaminant internal, external and internal exposure. There may be a question similar to that, where you have to do that kind of trade-off, including the APF for respirators. We have not done a ton of calculational work. We've done some throughout the semester. But I think the essential thing that separates health physicists from other safety professionals is that we are quite competent at a very quantitative aspect of safety. So radiation safety is more quantitative, more calculational than a lot of other kinds of safety work is. And so that's what I'm going to focus on, is the ability to do that kind of analysis for things that are very fundamental to health physics work, like external exposure and internal exposure. Okay.
I'd also argue we deal with the more obscure questions, because when you're dealing with normal safety, people have a concept that acids burn them and why that happens.
That's right. Public education is another part of it.
Yeah.
Okay. And the other thing is radiation is tasteless, colorless, invisible, and so it's they can see the chemical in the flask. They can't see the radiation coming out. So that I think that's a part of the mystery involved. Okay, I don't want to keep you all night. You have other things to do. I think I've told you what you want to know, especially about the exam. So look over the video I did. I don't think I've put that video on YouTube yet, so I need to do that. And I'll put this video on YouTube and we can go from there. Okay? Go ahead.
When are you gonna make the test available?
That's a good question. When would you like the test to be available? I try to give people a week. I have to have these things in. Maybe Monday.
Okay.
Okay.
And it'll be available Monday to Monday or Monday to
Yep.
Friday. Okay.
Let me see. I think I have a little bit more time than that to get them to the registrar. I don't remember, so I'm going to move this. Oh, if I stop sharing, yeah, I did. So I can leave this over here. I want to find out when I have to have it in. So this is spring 2023. So Monday will be what? Monday will be the 1st. Yeah, that gives me plenty of time. So, well, yes. So Monday to Monday, I think is what we'll do. Okay.
That sounds good.
Actually, the final exam period is supposed to be May 1st through 6th, but I'm going to give you guys the extra Sunday to work on it as well. Okay. So Monday to Monday. Just don't report me. Okay. Anything else I can help you with?
Are you going to go over the problems that were missed on the second exam?
I thought, well, have I not done that?
I don't remember you doing that. I mean,
Well, you weren't, I think you were, you
Did I
might have
say-
been gone last time. So look at that video and then email me if you have questions. I did discuss the calculational problem we had last time and the places where a number of people had questions.
Okay, I must have missed that.
Yeah, I think that, yeah. Okay, yes, I did. Yes. And if you have questions, feel free to email me or call me or text me or whatever it is, and I'll try Discord or whatever, and I'll try to get back to you about you individually. In the video, I did it fairly with no names, let's say. So, other questions? It's been a pleasure this semester. I've enjoyed particularly this small group who tends to gather here. I like the interaction. I wish, as much as I can, that we were able to do this face to face, but you guys are scattered and I understand we have to accept life as it comes. Okay, have a great final exam. Do your best, you'll be fine. I have every faith in you. Have a great summer. If I see you over the summer, wonderful. If not, I hope to see you in the fall. And I'm looking forward to working with you again.
Thank you.
Bye-bye.